Earthquakes are one of the most commonly known natural disasters which have accompanied humankind for thousands of years. In reality, not all damages caused by earthquake result from ground movement directly. Instead, the collateral damages such as flooding and fire resulting from ground movements are more catastrophic to people, especially those who lived in crowded cities. For example, in 1906, the fire started by the Great San Francisco earthquake burned the city for 3 days and left 250,000 people homeless. More than 4,000 earthquakes are happening each year in Canada, and the principal region for the seismic activity is around the coast of British Columbia. During an earthquake, the ground movement can potentially damage the gas and power lines in a household. The spark generated from the broken electric wires can easily ignite the leaked gas and create a fire hazard in the house. Thus, a method to minimize the damage from earthquake fire hazard is required. In this project, our group decides to design a system that reduces the collateral damage of the fire hazard resulting from the broken gas and power lines in a household after the earthquakes. Since people will prefer the system design to be inexpensive and affordable, the first objective for the design is to reduce the total system cost under the budget limit of $500. Besides the design cost, customers also prefer a simple implementation of the system on the electrical and gas systems in their house. After comparing the dimensions of same seismometers on the market, we set the system's maximum size to be 0.05 cubic meter as the second objective. Finally, the system should accurately detect earthquake and only triggers if the magnitude of the seismic wave passes the threshold, which is 6. To better evaluate the detection system's accuracy, we create an evaluation matrix shown on the right side, which lists all the possible outputs of the detection system. As a result, the system design's final objective is that the detection system should have a minimum precision score of 60% and a minimum recall score of 90% with the given threshold. The precision and the recall formula are shown under the evaluation matrix on the right side. In order to implement the system on the power and gas systems in a household, it has to withstand the current and the gas pressure from a typical household. Thus, the first system constraint is that the system can at least withstand 100 amps of current and 420 kPa of the gas pressure. Additionally, the second constraint is that the system must automatically cut off the electric and gas supplies during an earthquake without any human interactions. Finally, after the system has been triggered and cuts off the electricity and the gas, there must not be any leak in both lines. Therefore, the last constraint of the system is that after cutting off the electricity and gas, the current in the power line has to be 0 amp, and the pressure in the gas pipeline also has to be the same as the atmosphere pressure at 101.325 kPa.
So when the system is online, it will first determine the latitude and longitude of the city chosen. Then based on the coordinate, it will fetch real-time waveform data from all monitoring stations in that region. It will fetch 1 minute of data with 30 seconds for the online server to respond. An extra file will be found as a sign that data is available. If not available, it will try to fetch the same data for 8 more times. If still not available, it will move on to the next cycle. After data is found, it will compute the magnitude. If it is greater than 6, then the system will be triggered to cut off supplies. If no earthquake is detected, the system will continue running. The system doesn't need human interaction, which will be proved in our demo video later. Precision represents the probability of making detection when an earthquake happens. Recall represents the probability of making correct detections instead of false detections. We require a precision of over 90% to make sure the system will be triggered during an earthquake, while the recall is set to 60%. To compute precision, we collected 30 past earthquake events. All have a magnitude of above 6. We noticed that the system may underestimate the magnitude, so we set the magnitude threshold to 5.5. We ran our detection algorithm on the test set, and we reached a precision of 100%. For recall, we ran our program for a day in the Waterloo region, and no false detection was made. To further quantify it, we consider detections that overestimate the magnitude for above 0.5 as false detections. The same test set returns a recall of 90%, which meets the objective.
So for the hardware solution, we are using a Raspberry Pi for running the earthquake detection algorithm, which will send the signal to this relay module in case it detects an earthquake. So this would be step one. So for step two, then this two-channel relay module receives the trigger signal from the Raspberry Pi, and it will send this trigger signal to both this contactor and the solenoid valve. Uh, so once contactor receives signal from the relay module to shut off, it shuts off your house's electricity supply. And same would be the case with the solenoid valve. So once it receives the signal from your relay module, it will shut off the gas supply of the house. So once an earthquake would have passed, relay module will energize both the contactor and the solenoid valve, and which will restore the power and the gas supply to your house. So once your earthquake is gone, everything would be turned on back. So that would be your last step. So this shows the wiring diagram. So here we have the Raspberry Pi module, here we have the relay module, and here we have the relay module connected to the solenoid valve and the contactor through 110 volts AC. So the contactor and solenoid valve both are powered from 110 volts AC, which passes through this relay module.
The whole system includes a Raspberry Pi 4, a 100 amp contactor, a solenoid valve, a relay, and a battery as the external source. Only the contactor is different from what we used in our prototype to withstand a higher current. All items add up to $379 and 0.00282 cubic meters, which meet our objectives.
So coming to the durability constraint, so the durability constraint is it should withstand at least 100 amps of current and 420 kp of gas pressure. So if you look at the data sheets of both the contactor and the solenoid valve, so for the contactor it says 100 amps, and here it also says 100 amps single phase, which means it satisfies the 100 amp constraint. And for the solenoid valve data, we can see the gas pressure on the datasheet says 0 kg per centimeter square to 7 kg per centimeter square. And if you if you convert this 7 kg per centimeter square to kPa, it becomes 686.5, which is greater than our threshold of 420 kPa, which means the valve satisfies our 420 kPa constraint. And for the effectiveness, the constraint is the current in the power lines has to be 0 amps, and the pressure in the gas pipe has to be the same as the atmospheric pressure, which means both the contactor and the solenoid valve should be able to completely cut off our gas and electricity supply.
Now I will do a demonstration of our system in a real-life working environment. We connect the contactor to an extension cord with a lamp to show that it can cut the power supply. We use a hairdryer to simulate gas supply, and when the valve is closed, you will see that there is no air going through the valve. We didn't connect our system to our house to avoid accident that may cause serious physical damage to us or our neighborhood.
So as you guys can see, this is the Raspberry Pi board, which sends the signals to this relay module. And this is a two-channel relay module, which means this can control both the contactor and the solenoid valve at the same time. So contactor will control all your electricity supply in the house, and the solenoid valve will control the gas supply in the house. And now we're going to demonstrate each one of these to see how they exactly work.
The system will monitor earthquake data in the Waterloo region. From the console output, it correctly determined the latitude and longitude of Waterloo. Then it successfully fetched the real-time waveform data. The fetched waveform has been shown here. For demonstration purpose, the system will output true after running 5 cycles to show what's gonna happen in real life when an earthquake occurs. Since 5 cycles are a lot of time, we will clip the video and let's jump to the last cycle now. As you can see, we triggered the system and it closed the relay. There's no air going through the valve and the lamp is also closed, proving that our system can cut off supplies when an earthquake occurs. So that is all our presentation. Thank you very much.